Okay, to continue, for example, we have an input voltage for the positive half cycle of 10 volts and the negative 10 volts for the negative half cycle. At positive half cycle, output voltage is equals to 0 because the diode is shorted. At negative half cycle, the output voltage is equal to the input voltage because the diode is open. So basically, if the diode is parallel with the output voltage, when the diode is being opened, the reading of the voltmeter on the diode would be equal to the input voltage. And since there is no voltage acting on the resistance, so the uh, it clips the voltage at positive half cycle. Clamping network. Clamping. There is the presence of capacitor. Resistor and diode is parallel to the output voltage. So this is very important that in the clamping network, there is the presence of capacitor. For example, we have an input voltage of 6 volts for the positive half cycle and negative 4 volts for the negative half cycle. At positive half cycle, we have an input voltage minus the voltage at the capacitor is equals to 0, wherein the output voltage is equals to 0 volts since the diode is short-circuited. Therefore, there is no current passing through this resistor. So the input voltage would be equal to the voltage at the capacitor, which is equals to 6 volts. So at the negative half cycle, this diode will be open, therefore there is current passing through this resistor. So we will have our KVL, which is input voltage minus the voltage at the capacitor minus the output voltage, which is equals to 0. Our output voltage will be equal to negative 10 volts. So one of the most important principles for this clamping network is that the total voltage of the input must be equal to the total voltage of the output. For example, we have a 6 volts at the positive half cycle and we have negative 4 volts at the negative half cycle and we have a total of 10 volts. And our output voltage is equals to the negative 10 volts or 10 volts. Zener diode. It allows the flows of current in both directions. Unlike the ideal diode, it only allows the direction of current flow in one direction. Condition. The voltage must be greater than the required voltage for the diode to activate. And it can also serve as a voltage regulator. On this first example, we have a voltage source of 24 volts, a resistance of 1 kilo ohm, and a Zener diode which has 12 volts to be activated. So by applying the Ohm's law, 12 volts over 1 kilo ohms, the current passing through this circuit is equals to 12 milliamperes. For the example B, this is an example of a voltage regulator. We have a 16 volt voltage source and we have a 12 volts Zener diode. So the principle behind it is that whatever voltage source or whatever the amount of voltage source being inserted in the circuit, the output voltage would be equal to the voltage of the Zener diode or approximately equal to the voltage at the Zener diode. BJT transistor. BJT. Current control device. BJT terminals. We have three. The emitter connected to forward bias, the base connected to reverse bias and the collector. The types of BJTs, the NPN transistor and PNP transistor. For the NPN transistor, we have two N-types semiconductors with one P-type semiconductors. For the PNP transistor, we have two types. We have two P-type semiconductors and one N-type semiconductor. However, in the BJT, the common kind of transistor being used is the NPN transistor. Formulas that must be remembered. We have the alpha, which is equal to the current passing through the collector over the current passing through the emitter, and the beta, which is equal to the current passing through the collector over the current passing through the base. We could also say that the current passing through the collector is equals to the alpha multiplied by the current passing through the emitter is equals to the beta times the current passing through the base, as alpha is equals to beta over 2 beta plus 1, wherein beta is equals to alpha over 2 1 minus alpha. And the current passing to the emitter is equals to the current passing to the collector plus the current passing to the base. As we have the KCL, the current going in, the current going out at the emitter is equals to the current going in of the collector plus the current going in of the base. Example, we have a fixed bias circuit. We have a VCC as the voltage source, the RC at the resistor at the collector, the RB as the resistor at the base, and we have the current at the emitter, current at the collector, and current at the base. This is the simplest circuit, which is called the fixed bias circuit. We also have emitter stabilizer. It is just like the fixed bias circuit, however, there is a resistor at the emitter. Next, we have the voltage divider. In this case, there is two resistor at the base. So we must get the resistance, the impedance equivalent of the base, which is equal to RB1 parallel to RB2. And we must also get the voltage equivalent of it, which is equals to VCC times the RB2 over to RB2 plus RB1. Next, we have the RE model. So at the lowest part is the RE model of this kind of circuitry. It has the following fixed part, which is the BRE, the BIB, and the RO, wherein the RB is equals to the resistance of the base and RC is equals to the resistance at the collector. And we have also the input voltage and the output voltage. And this is very effective when we are and if we are needed to get the input impedance and the output impedance of the circuit. Lastly is we have the hybrid equivalent. This hybrid equivalent is just like the RE model, and its part has corresponding equivalence corresponding equivalence in RE model. For example, we have the HIE, which is equals to BRE at RE equivalent, and HFE, which is equals to the beta in RE model, and the HOE, which is equals to 1 over the RO of the RE model. So that's it for electronics 1. Thank you.